All right, let's dive in. We're going to talk about thermodynamics, the absolute fundamental rules that govern energy, heat, and work. Well, everywhere. From a massive steam engine all the way down to the simple warmth you feel when you rub your hands together. These laws are always at play.
So, let's kick things off with a bit of a puzzle. Think about this. You can rub your hands together, right? And they get warm. The work you're doing turns into heat. Makes perfect sense. But have you ever seen a table just suddenly get icy cold and use that energy to launch a book into the air? I mean, think about it. In both cases, energy is conserved, so what gives? Why does one of these things happen all the time and the other, well, never? That's what we're here to figure out.
Okay, to even start to unravel that puzzle, we got to go way back to basics and ask a really simple question. What even is heat? And trust me, the answer we have now is not what people used to think. For a long, long time, scientists were on a completely different track.
So, for ages, the best idea anyone had was this thing called caloric theory. They literally thought heat was an invisible fluid, this caloric that would just flow from a hot object to a cold one, kind of like water. But then, cannons. A guy named Count Rumford was watching workers bore out cannons, and he noticed something incredible. The friction was creating a limitless amount of heat, and that just didn't add up. How could a finite amount of fluid create infinite heat? It couldn't. That was the moment everything changed. Heat wasn't a thing at all. It was a form of energy being transferred, a total game changer.
And that brings us right to our modern definition of thermodynamics. At its core, it's just the science of how energy moves around, specifically how heat and temperature relate to work and other forms of energy. And here's a key thing to remember. It's a macroscopic science. That just means we're looking at the big picture stuff we can actually measure. Pressure, volume, temperature. We don't have to worry about what every single individual molecule is doing.
Okay, so if we're going to talk about energy moving around, we first need a way to measure what's happening, right? We need a yardstick. And that brings us to the first rule of the game, which is, weirdly enough, called the Zeroth law. Now, you heard that right. It's so basic, so fundamental, that after they'd already come up with the first and second laws, they realized they missed one and had to go back and stick this one in at the beginning.
The whole idea of the Zeroth law rests on this one concept, thermal equilibrium. It's super intuitive. You put a cold can of soda on your desk. What happens? Heat from the room flows into the can, but it doesn't do it forever. Eventually, the can and the room are the same temperature. Everything just settles. When all the measurable stuff, like temperature, stops changing, boom, that's thermal equilibrium. They've reached a truce.
And the logic behind this law? It's almost so obvious it feels weird to say it out loud. It's just this. If object A is the same temperature as object C, and object B is also the same temperature as C, well then A and B have to be the same temperature as each other, right? It's that simple, if A equals C and B equals C, then A equals B, thing we all learned in math class. And that simple, common sense idea is the absolute foundation for how we measure temperature.
So here's the big takeaway, the whole point of this law. It gives us a real solid definition for what temperature actually is. It's not just a feeling, ooh, this is hot, or brr, this is cold. Temperature is that one specific property that's equal when things stop exchanging heat. It's the reason a thermometer works at all. It's the universe's ultimate equalizer.
All right, now that we know how to measure things, let's get to the first law. And if the Zeroth law was about finding balance, the first law is all about the money. Or, well, the energy. Think of it as the universe's super strict accounting department. And this simple little equation is the whole budget. It just says that when you add heat to a system, that's delta Q, that energy can only do two things. It can either get stored inside the system, which we call increasing its internal energy, or delta U, or it can be used to do work, like pushing a piston, which is delta W. That's it. Energy in has to equal energy stored plus energy spent. Nothing just vanishes. The books always have to balance.
So let's drill down on that internal energy thing for a second. The easiest way to think about it is like a bank account for the system's molecules. It's the sum of all their random jiggling energy. When you add heat, that's a deposit. When the system does work, that's a withdrawal. And here's the really important part. The universe only cares about the current balance. It doesn't care how it got there. That's what we mean by a state variable. All that matters is the state it's in right now.
Okay, this all sounds a little abstract, right? So let's make it real. Let's look at that energy budget in action with something we've all seen. Boiling 1 gram of water into steam.
Okay, first step, the deposit. To turn that single gram of water into steam, you need to add 2,256 joules of heat. That's our starting capital.
Now, as that water turns into steam, it expands a lot. It has to push the air around it out of the way to make room for itself. That takes energy. That's our first withdrawal from the account. About 169 joules is spent just on doing that work.
So what happens to the rest of it? Well, the remaining 2086.8 joules goes directly into that internal energy bank account. It's the energy that makes the water molecules themselves go crazy, zipping around as a gas. And look at that, the budget balances perfectly.
Okay, so the first law is awesome. It tells us the book's balance, energy is always conserved. But it still doesn't explain our original puzzle, does it? It doesn't tell us why a book can't just suck heat out of a table and fly into the air. For that, we need the second law. This one doesn't care about the accounting, it cares about the direction of traffic. It's the law of the universe's one-way streets.
So one way to put the second law, this is the Kelvin-Planck statement, is to talk about engines. And it's basically saying you can never ever build a perfect one. It's impossible. You can't just take heat from a fire and turn 100% of that heat into useful work. There's always going to be some waste heat lost to the environment. A perfect, 100% efficient engine is a fantasy.
And here's another way to say the exact same thing, this time from Clausius. It's all about how heat flows. And it just says that heat will never, by itself, flow uphill. That is, from a cold thing to a hot thing. It's so simple, right? It's why your hot coffee gets cold. But it's also why your glass of ice water will never start boiling by sucking in heat from the air around it. It's a one-way street.
This is it. The second law is the cosmic cop that says no to all these things that the first law's balanced budget would totally allow. It's the reason a broken egg doesn't just put itself back together. It's why the air in your room doesn't just decide to all huddle in one corner. And to answer our first question, it is the fundamental reason why a book will never use a table's heat to launch itself into the air. The universe has a preference. It moves from order to disorder, and it never goes the other way on its own.
So, okay, we've established that a perfect, 100% efficient engine is impossible. But that begs the question, what's the best we can do? What's the absolute theoretical speed limit? Well, to figure that out, we need to talk about a really cool thought experiment, the Carnot engine.
Yeah, way back in 1824, this brilliant French engineer, Saudi Carnot, sat down and imagined the most perfect engine possible. One with no friction, no heat loss, where every single step could be run backwards perfectly. Now, you can't actually build this thing, of course, but as an idea, it's genius, because it gives us a hard and fast number for the maximum possible efficiency of any engine. It's the ultimate cosmic speed limit.
So how does this perfect engine work? It runs on this beautiful four-step cycle. Step 1, you let gas expand while keeping it at a constant high temperature. It absorbs heat and does some work. Step 2, you let it keep expanding, but this time you insulate it so no heat gets in or out. This makes it cool down. Step 3, now you compress the gas at that new lower temperature and it releases its waste heat. And finally, step 4, you keep compressing it, again with no heat exchange, which warms it right back up to where you started. It's this perfect, elegant loop.
And here's the absolute kicker, the whole point of this thought experiment. The maximum possible efficiency of any engine you can ever dream of building. It doesn't depend on what fuel you use or how clever your design is. It boils down to this simple formula. It only depends on the temperature of your hot source and the temperature of your cold sink. That's it. The bigger the temperature difference you can create, the closer you can get to that ultimate cosmic speed limit. So we've gone all the way from why your hands get warm to the ultimate limits of an engine. And what we've seen is that while energy is always accounted for, the universe itself seems to have a direction, a one-way ticket towards messiness, towards disorder. Which leaves us with a really deep final thought. If a broken egg never unbreaks and a cooled coffee never reheats, could it be that this relentless, unstoppable march towards disorder is what we experience as the arrow of time itself? Something to think about.